Hello everyone, and thanks for checking out the second part of the project management videos. If you have not seen the first video, which is the one that's on the planning and scheduling of projects, then you may want to check that out. And so at the end of that video, I ended with how we use networking to be able to schedule um, different activities within a project and figuring out slack time so that we can figure out where our critical path is for our project, which is the activities that must be done and must be done on time so that the project does not get delayed due to bottlenecks. So now what we are about to do is get into more of the PERT analysis, which is again, PERT means program evaluation and review technique. So we're at the point in the project life where the planning and the scheduling is done, and now we're actually going to implement and uh, sort of do a feedback loop to say, hey, this is how this is going. If we need to make some adjustments, we'll make those. But before we do that, we need to also figure out realistically how soon can we finish this particular project. And so to give you the backdrop from the first video, we had a company, General Foundry, and they produce steel. And the EPA, their local EPA, has summoned them to install a highly sophisticated air filtration system so that they can be up to code as far as pollution standards and all that. And they have roughly 15 to 16 weeks to be able to get this implemented, or their operations will be shut down. And so right now the company is doing the planning and scheduling of trying to get that particular project going, trying to figure out all the activities and such so they can get it done. We're now at the point to where we know that ideally we want to get this done in 15 weeks, but we need to see how realistic that is. And so when we do PERT analysis, um, what we're basically trying to do is add in probability to this. And so we look at the 15-week mark as sort of the mean or the ideal case. But we also want to look at two different times. And so this is called the optimistic time, meaning if we can finish the project early, how many weeks would that be? As well as the pessimistic time, which is if we run into some problems that we sort of guess might happen, how long would that be? And what we want to do is assign a probability or a percentage um, to that so that we can say, all right, well, if you give us 15 weeks to do it, then we know that we're confident up to this level that we can finish it. So let's say 15 weeks, we're 50% confident we can do it. If you only give us 13 weeks, then maybe we're only 30% confident that we can do it. If you give us 17 weeks, then we're 99% confident that we can get it done. And so that's kind of the thing that PERT analysis, as far as throwing in the probability into it, allows us to be able to do, or allows us to be able to see. And so now we're going to see how that actually comes into play. And again, we want to come up with an optimistic time, a pessimistic time, as well as our most likely time. So these are things we are considering here. Now, when we do the PERT analysis, we want to get the expected activity time, which is just going to be T equals A. And if you remember, let's go back here. A is our optimistic time. On average, if we can finish early, how many weeks is that? And then we have the 4 times M plus B, and B is the pessimistic time, all that divided by 6. And so what we're actually doing here when we calculate this, In terms of probability and statistics, what we're actually doing is, in a way, figuring out a standard deviation. And I want to go into a little bit of detail as to why that is. If you see here, the most likely time is weighted at 4, whereas the optimistic time, which is here, the A, and the pessimistic time only has a weight of 1. And you notice that this is being divided by 6. Now, if we look at a probability density function, mainly our bell curve here, we know that our mean time is going to be right here in the middle. And so normally whenever we look at standard deviations, we look at 3 standard deviations below the mean and 3 standard deviations above the mean. And if we're looking at it that way, then you see we have 1, 2, 3, 4, 5, 6 different areas that we're looking at here, okay? And that's one of the reasons why we're dividing by 6 there. And they're saying that the most likely time is weighted here, so we think we have a better chance of being somewhere within, I think I've drawn that wrong. So within these 1, 2, 3, 4, yeah, I think I didn't put that out enough. So we think we have a better chance of being either in here, in here, in here, or in here, as far as the most likely time that you will fall in there. So that weight on 4 is basically saying this is M, and we're thinking that, you know, A may be somewhere here, B may be somewhere here. So that's sort of the idea of why we're taking this and dividing it by 6. The variance is just the difference in between the pessimistic and the optimistic time, and we're dividing it by 6 and then squaring. So it's just basically the standard deviation squared in a sense. And so here, this is the actual standard deviation, and that's why we're dividing this by 6. But the reason why I said here that this is sort of like us trying to calculate a standard deviation is because we have this weighted here. So if we weight this and then divide it by 6, then the time that the expected activity time that we get is going to be on average what we're actually expecting to get, okay? But here with the variance, this is just gives us sort of the range of fluctuation in what the time is going to be, and the standard deviation is actually what these different lengths are. So we know, let's say here to here, that is one standard deviation. That's another. That's another. That's another. That's another. That's another. And so when we look at that, those standard deviations, we are taking the times of the project as a whole and basing it upon solely on the information that we have about the best time, the worst time, and the most likely time. What is going to be the span of weeks or the time in which we can divide up the different times in which we are expecting to finish as a classification. And so this is very similar to, let's say we're in this course, right? So we're talking about who's going to make an A, who's going to make a B, who's going to make a C, who's going to make a D. And so based upon if we graded this course strictly off a bell curve, then there will be a certain number of people who make A's, certain number of people who make B's, C's, D's, F's, whatever, okay? And all that is classified solely upon who scored the highest, who scored the lowest, and how many people scored in between. And so that's sort of the idea of standard deviation. So we're just trying to find a way to classify if we're within this particular time range in weeks, how far from the mean do we actually fall? And the standard deviation is just the length of each one of those classes. So this is what our probability density function would look like if we actually sort of draw it here. And we see that the most likely time is here. And we see that this is has a right tail to it. So there's more of a chance for us to have a time later than what we expect, other than the time that's going to be a little bit better than what we expect. Okay. And so if we were to try to see what's going on as far as the optimistic time, most likely time, and the pessimistic time here, you see all these columns or all these cells in yellow are how we're calculating. So to kind of show you how this goes for activity A, we're thinking that it's going to take us about 2 weeks to complete it. If we can get it done early, we can get it done in a week. If we find some issues or we have some hiccups, it's going to take us about 3 weeks. And so this is part of what we would have to decide during the planning and scheduling phase. And if we have that, then of course, if we do our calculations here for the expected time, and of course, remember, the expected time is going to be the A plus 4M plus B, all that divided by 6, then that's going to be 2. Our variance is going to be 0.11, and our standard deviation here will be 0.33. So what this communicates is our expected time for that particular portion is going to be about 2 weeks. And based upon what happens, we know that we're going to vary about 1/10 of a week, and our standard deviation is going to be about 1/3 of a week. Okay, so if we looked at that, this was 2 right in the middle, then 1 standard deviation to the left would be 2 minus 0.33, which would be about 1.67, and then 2 standard deviations off, that'll be about 1.33, and then this will be 1, and so on and so forth. If we go up here, this would be 2.33 if this is 1 standard deviation above, 2 standard deviations above, and then 3 standard deviations above the mean. And so this is how we would divide up everything. And our variance here is about 1/10 or 11% of a week, roughly about 1/10. So about a day or two, and finishing it. And of course, we would do that for all of these separate activities here. So everything that you see in the yellow cells is what we would have to come up with based upon what our guesses are from past experience. And then from that, we would make these calculations for standard deviation, variance, and the expected time. And of course, the expected time is what we would use in our scheduling. So the actual project variance, which is the sum of all the different variances for each activity, we would see that that ends up being about 3.11. And of course, if we took the square root of that, that would be about 1.76. So what this is saying here is that each activity, if we take the sum of all those things and figure out what the variance is, and then take the standard deviation, we're saying that this particular project, when we categorize it into its different classes, we think we're going to finish, and I'll just draw something up here. Ideally, we want to finish within 15 weeks, but based upon certain percentages, we're going to classify the times in which we finish at about 1.76 weeks out. Okay, so make this a little bigger so that we can get a better idea here. So if this is 15 weeks here, then if we do 15 minus 1.76, that would be what we would have here. So it's like 13.24. And if we went up one standard deviation, that'll be about 16.76. And so what we know about probability density functions, and particularly the bell curve, about 34% of all your data is going to be here, and about 34% is going to be here. So somewhere in between 13.24 weeks and 16.76 weeks, according to what we see here, we have about 68% confidence that we can actually finish that project within that time period. So that's kind of what this is saying. Now, what this Z here is this is what the corresponding Z score is. And from probability and statistics, this is the formula for it, which is the data value minus, in this case, the population mean divided by the standard deviation. And so when we do that, we actually get what the corresponding Z score is, and what the Z score is an equivalent of saying this data, but it's written in such a way to where it is one standard deviation. Well, it's written in terms of standard deviations above or below the mean. So kind of translate here, 15 weeks would be similar to saying a Z score of 0. And here at 16.76 weeks, that would be the same as saying a standard deviation, a Z score of 1, because 16.76 weeks here would be exactly one standard deviation above the mean. The 13.24 weeks, that would be exactly one standard deviation below the mean. And of course, if we wanted to figure out what it was at 16 weeks, you see that we have this number 0.57, which is somewhere along in here. And so 16 weeks would be about 0.57 weeks above the mean, okay? And here we can actually figure out what the percentage confidence we would have in finishing the project based upon what our probability density curve would tell us. And so I'm going to pull up a particular chart that's going to help us be able to come up with this. All right, so what I have here is a standard normal distribution table, and of course this is our probability density function here. And the probabilities that you see, the numbers here are just probabilities, or the area under the curve of this. And here we said that 16 weeks actually equals about 0.57 standard deviations above the mean. So when we come here and read this, we actually split this out to be 0.50 plus 0.07. And based upon these two numbers here, we're going to find the intersection of that in this chart so that we can see what the probability is, or the area under the curve. So if we go here to the 0.50, and then this is 0.07, if we look down where they intersect, of course this is going this way and this is going this way, we see that we have 0.7157, which tells us that if we can get the project done in 16 weeks, then we have basically a 71.57% chance that we can get the project done. Okay, and so that is what we were referring to when we talked about from Appendix C what the corresponding um, confidence of completion of the project would be if we said that it would take us 16 weeks to do. Now, the purpose of this is, remember, the EPA is making us do this. And by what I mean by us is the General Foundry Company. If we presented to the EPA, hey, we planned everything out and we know that you want this done in 15 weeks, but if you give us 16 weeks, then we have a higher percentage of confidence that we can get this done based upon our planning. And if you notice, right at 15 weeks, we only have a 50% chance or 50% confidence that we can get it done. Of course, if they allow us to extend it out to 17 weeks, 18 weeks, then of course there's a higher probability that it'll get done. So we can bring this information to the negotiation table so that we can sort of negotiate on how long we actually have to be able to install this air filtration system. And so this gives us the probability of completion here. So now you see where that comes from. And of course, we want to get it done in 15 weeks. Standard deviation is 1.76 weeks. And we see at 16 weeks, we know that this area under the curve here is 0.7157, which basically says we think we have a 71.57% chance of getting this done 16 weeks or less. And of course, if we wanted to get 99% probability of getting it done, we would need to be able to extend that out to a little more than 19 weeks. All right, so let's switch gears here and start to talk about managing project cost. And we mentioned this earlier in the video, but once we know how much each activity takes to be able to get it done, of course, we're looking at the cost over the overall project. So we're looking at the sum of how much all those activities are going to cost. And we want to monitor that weekly. And as we monitor that, we're sort of going to do this in a linear fashion. So the example that I had said in the beginning was, if we have a project that costs, let's say, $100 million, then if we're going to do it over a 10-week time span, then we want to make sure that we don't go over $10 million a week. Of course, if we have some instance that comes along that slows up the project, or if we find that, hey, we don't have all the resources that we have, we may end up having an overrun for that particular week. But of course, we want to try to find ways to mitigate that. And normally that would mean pulling in extra resources or pulling off resources off of non-critical activities and putting them on more critical activities so that those critical activities can be done on time. And so we're going to see how knowing about our earliest start time, earliest finish time, latest start time, and latest finish time, how we can actually manage that. And so in the budgeting process, of course, again, we want to identify all the costs of each activity, and then we want to identify how the cost will actually be spent, and we're going to use earliest start time and latest start time to determine how the money has been spent. So if we look at our project here, cost-wise, we see that for activity A, it cost us $22,000 to get that complete. Activity B is $30,000, and move on down the line, and we see that project H, or activity H rather, is $16,000. And of course, we get this budgeted amount by looking at the total cost divided by the number of weeks we expect the particular project to last. So for activity A, it's 2 weeks, so 22,000 divided by 2 is just 11,000. Of course, activity B is expected time is 3 weeks, and so 30,000 divided by 3 is 10. So that's how we get this column here. And if you don't remember, we got our expected time by doing the optimistic time plus 4 times the most likely time plus the pessimistic time, all that divided by 6. And we went over already why it is that we're actually dividing by 6. We're doing sort of like a 80% 10%, 10% weight on the optimistic time, most likely time, and pessimistic time. And again, we see that the total cost is going to be $308,000. Okay. All right. So the last thing that I want to talk about here is we also have our earliest start times and our latest start times shown here. And so, of course, we need to see this because this will let us know where we have some wiggle room. Also, we can see how many projects are going on simultaneously. And so that's what we're going to see here in the next few slides. So looking here, you see if we lay out all these activities, list them week by week, you'll see that for all the activities that are in red, these are the critical paths. So we must spend these particular dollars in the week that is specified. So for activity A, we have to spend the total $22,000 within weeks 1 and 2. For activity C, we're going to have to spend those $13,000 in weeks 3 and 4. So no way of getting out of that with the current setup. And so you'll see here for week 1, we see that our total amount we spend is $21,000. And of course, the cumulative amount, which is total to date, of course, for week 1, we just have 1 week. So that's why it's $21,000. If we move on to week 2, we see that, of course, another $21,000 needs to be spent. And the total amount we spend here is going to be $42,000 at that point. And then for week 3, we see an additional $23,000 needs to be spent. Activities 1 and 2, activity A is over for weeks 1 and 2, but we see now we're ending activity B and starting project C. So that's where the money is being spent there. And of course, the cumulative amount will be the $42,000 plus the 23, which gives us 65. And we kind of see as we go on and on and on, how when we get towards almost to midway through, how we're spending the most amount of money there because we have a lot of simultaneous activities going on. And we see that E is the one that's critical here, whereas D and F are not critical, but of course we still want to get them done if we can. And so you can see here how we're just getting our cumulative amount, and of course the totals here should equal the total there once done. All right, so this slide just shows how we have the activities here. Activities A and B, of course, they have no immediate predecessors, but activity C has A, activity D has A and B as its predecessor, so on and so forth. So I just put that there to make sure that you know how all the activities were aligned as far as what comes before and what comes after. And of course, if we use the latest start time, then of course, all this is shifted some. And so to make sure that we kind of understand what's going on, if you notice, we started off using the earliest start time, okay? And so with that, the way that we spend is a little different. If we use the latest start time, we're basically going to delay activity B here. So if you see activity B used to be right here, but now we shifted it up 1 week. And so now how much money we actually spend is going to be a little different. We also see that for activity D here, do you see how it's aligned directly and running at the same exact time as activity E? But if we go back, we see that activity D actually started a week before activity E here in this case. But by us doing the latest start time, we actually push everything up for activity D 1 week and have everything aligned with activity E. You also see that for F, which is another non-critical activity, this got pushed way up to week 11, starting week 11. If we go back and look at the earliest start time, F started at week 5. So if we use the latest start time, then we can actually delay activity F by 5 weeks, 5 weeks or so, actually 6 weeks to be exact, before we can start working on this. So again, the point of this is just to show if we use the earliest start time, the rate at which we spend money is going to look different than using the latest start time. And of course, if we were to graph that using the earliest start time and the latest start time, this is what it would look like. And so the thing that we are most concerned about here is the gap that's in between. And so we see, based upon using earliest start time and latest start time, if we use the earliest start time, we're going to be spending more money faster. Whereas if we use the latest start time, we're going to be spending more money later. And this gap here represents the difference in how much money we're actually going to spend at a particular moment. So to make sure that we're all on the same page here, I'm going to erase these. And let's say at week 8, the difference in between here and here, I'm just going to estimate this may be like at 170,000, and this may be at 200,000 here. So that difference there is $30,000. And a reason why we would want to pay attention to this is because, let's say, if we have to do this during a particular season within our business, to where we have to pay, let's say, a lot of property taxes, or we have to pay insurance, or we just have a lot to pay back at a particular time, we may want to use the latest start time so that we can reserve some actual cash, so that we're actually spending money in later weeks, because in later weeks we may get some of our accounts receivables back, and from there we actually have more cash actually in hand to be able to pay for the expenses of implementing this air filtration system. Whereas if we use the earliest start time, we may have an instance to where, let's say, we're good as far as cash is concerned. This is a season where we're not at the end of a quarter, so we don't have to pay, the quarterly taxes, or we don't have the, insurance payments, or the payments for, legal type stuff that may not be due during a particular time period where we're doing this particular project, so we may actually have more cash on hand. Okay, and so that's what these graphs are good for. Now, we also want to be able to calculate what's going to be the value of the work completed at any given time in the project. And so how we do that is we take the percentage of the actual work that's done, and we multiply that times the total budget for that particular activity. Okay, and of course the cost difference will be whatever the actual cost is from whatever the value of the work completed at that particular time. And so if we look here, we'll see that for we'll just take activity B, for example. The total budget for it is $30,000. It is 100% complete, so the value of the work is $30,000 at that point. Now, the actual cost, we see it was $36,000, so we ran over $6,000. Now, that's sort of mitigated a bit by looking at project A, which is also completed, but we actually saved $2,000 there. Okay, but as you can see, if we go down the list for the activities, we planned to spend this amount of money, but we see in activity B and activity D and activity E that we had to overrun for some reason. But for activities A and F, we're currently underrunning. In other words, we're currently under budget. Okay, and we see for activity C, we were actually on budget for that one. So in looking here, we can kind of get an idea of, in general, how much we're overrunning. And then, of course, with the amount of weeks left in a project, we could look at some activities and say, all right, well, is there a way for us to be able to cut cost here so that we can still stay within budget? And so what we'll talk about here in a second is project crashing, where we actually look at what we have left, see if we can compress that time and possibly move some extra resources or acquire some more resources to be able to get those activities done faster and in a more cost-effective type of way. Even though it may cost us more up front, it may cost us less in the long run. Okay. Now, for, let's say, activity E here, we see that at this particular snapshot in time, activity E and F are running, and activity E is 20% complete. And so the value of the work there is just going to be, the 20% of this $56,000. So of course, 10% of $56,000 is 5,600. So 20% is that added 2 times. And of course, if we add all that together here, we get the 11,200. So that's how we're getting that amount. Of course, the actual cost is $20,000. So right now it says the difference here is going to be 8,800 here. Okay. So that's just letting us know where we're currently at. If we keep going at that particular pace, that we may overrun here. Okay. And so actually, since the actual cost is 20,000, we are actually overrunning. So the value of the work is this, but we're actually spending this much. So we're actually overrunning at $8,800 at that point, which is not good. But anyway, so again, this gives you a snapshot in time to kind of let you know what's going on with the project. And so using this information, you'll be able to figure out, all right, well, what other options do we have to be able to either rein in costs or be able to bring in extra resources to sort of wrap this up so that we can keep it under budget towards the end. So from being able to look at the numbers and see what we're overrunning, underrunning, we also need to be able to look at what our support staff is, so what our actual resources are for each activity to get this thing done. So we see what that is, and we need to take all that into account as well, because let's say for some of our non-critical activities, we may need to pull off 1 or 2 resources from those to add on to the projects that are in the critical path. And so now, if we're using the earliest start time, now that we know how the money's being spent, we can also do the same thing and sort of figure out how many people are going to be used, or how many of our resources are going to be used per week. And of course, this is like an indirect way to track the amount of money that we're spending, because of course the more resources that we use, especially if they're people, then the more is actually going to cost us. And so that should make total sense. Again, just like how we did with the cost per week for the budget, we see here that we're using this many people per week. So that's why for activity A, it lasts 2 weeks long. We're still using those same 4 people. Okay. And so now if we sort of map all that and put it on a graph, then we can kind of see that, hey, we start off not needing very much, well, I shouldn't say not needing much, but we need a good amount of supporting staff to start. But of course, we have an increase here, have a slight decrease, and then we have the highest that we're going to have during weeks 5 and 6. And then after that, it dramatically drops off here. And so if we look at it this way, then we can kind of say, all right, well, during weeks 5 through 7, what we have going on may not require so many people. So we could assign those people or those other resources to other areas, to help us out. Okay. Whereas we know that in the first weeks of the project, coming up to like week 6, we're going to need as many people as we can, relatively speaking. So we may have some other projects that we want to delay. Okay. So now let's talk about project crashing. So project crashing is basically trying to figure out how to reduce a project's duration, as well as trying to be cost effective in doing it. So in that, we want to figure out what our crash time will be for the project and for each activity. Also, we want to know the cost of crashing, because if we're pulling other resources in to be able to get a project done sooner, then it may end up costing us more for a particular activity within that project. And so we make the choice to crash a project based upon whatever the permissible amount is. So how much wiggle room we have as far as money is concerned, our due date, and of course, we want to keep those costs down as much as possible. Now, to crash a project, then what we want to do is these 4 steps. So the first thing is we want to compute the crash cost per period. Okay, and of course, we're going to look at each activity, break that down, and then from that, calculate what the crash cost per period will be for each activity, and then add that up to see what the total project crash time is going to be. We also want to find the current critical path and critical activities, and so we've already identified those for this situation. And then we want to find the lowest cost way to crash the critical path by one time period. So this is where the linear programming actually comes into play. Then afterwards, we want to update all the activity times, and if we need to crash again, then we'll do so. And so again, the crash cost per period is basically what the crash cost is going to be minus the standard cost over the difference in between the standard time and the crash time. And so we'll look here at this table here as an example. So of course, we look here, crash cost per period is crash cost minus standard cost, okay, over standard time minus crash time. So here we have the crash cost minus standard cost over the standard time minus the crash time. And if we look here for activity A, we're going to see how we get the 750 here. The crash cost is 22,750, and the standard cost is 22,000, and our standard time is 2 weeks. Crash cost is 1 week. So of course, the difference in the numerator is just 750. Difference in denominator is 1, and that's how you get 750. And of course, we follow suit for all of the activities, and that's how we get the crash cost per week. And of course, the ones that are highlighted in red are the critical paths. In other words, these projects have to be done in the week that we have them scheduled in order for everything to work out okay. Now, this is just an example of us doing a crash time here for, and let's go back and see which one that is. So for activity B, that's what that looks like, because they have a crash cost of 34,000, standard cost of 30,000, and the difference in between the standard time is 3 weeks, and we want to get that down to 1 week. So you see here that that's why we end up with $2,000 a week that we would have to pay to basically crash that particular activity for the project. And so now with us crashing this particular project here, of course, we still need to identify what the critical path is. So the activities that show potential bottlenecks, if we don't get them done on time, we still need to identify that. And then, of course, part 3 is we use linear programming to crash the project here. And so for those of you that are taking my course, of course, you have Excel files that sort of allude to this, and the ones that I'll show here, you actually have those available to you. If you don't have these, then of course, if you've been watching the videos before in week, I believe it's 1 or 2, you have a link that you can go to where you can pretty much just download all of these Excel files. So when we do linear programming, it's useful for crashing large projects, and it's a good way to kind of keep everything together so that we can calculate that without having to do a lot of tedious calculation by hand. And so for this particular situation, our decision variables are going to be the time at which activity I, or whatever activity it is within the project, is going to start, and C sub I is going to be the number of periods by which the activity is crashed. So how much we're trying to reduce the length of the project. And of course, our goal here is to do that with minimal crash costs as possible. And so if you look here, the 750, 2,000, 1,000, all of that is coming from the current crash cost per week. And so if we're going to crash making sure that this times the number of weeks we need to crash is going to be as small as possible. And so that's where this objective function actually comes from. All right, and so now, subject to all our constraints, of course, this first one here just says that activity A precedes activity C. So here the time that it takes to do activity A, and then that's going to be plus 2 minus the time that we want to crash activity C by, and that's going to kind of let us know when activity C is going to start. Okay, because if you remember here, the time at which activity I starts is T sub I. So here we need to know what's going to be the time for project A to start, and then plus, is it going to be 0? Is it going to be 1? Is it going to be 2? Okay. And then of course, same thing for activity A precedes D. So of course, whatever time activity A starts plus, and then of course, here this 2 is for the expected time minus the amount that you want to crash this by. And of course, we'll follow suit for all of these situations here. And of course, the numbers that you see here are the corresponding expected times. So for instance, we know that for activity D, that expected time is going to be 3 weeks there. So let's go back and check that. Okay, and I think we said here that activity B, standard time is going to be 3 weeks there. And if we go back here, just to be sure. Yep. So activity B, the expected time is 3 weeks there. So that is why we have the 3 here. And of course, all of the expected times would go right here in this column. Now, of course, for the amount of time that we want to crash, of course, activity A is 2 weeks long, so we have 1 week or less to crash that. For activity B, it's 3 weeks long, so we only have 2 weeks or less to crash that, and so on and so forth. And once we're done here, we know that for project completion is going to be the time at which we start activity H plus 2 minus whatever time we actually crash, or how many weeks we decide to crash activity H. And of course, that's got to be less than or equal to 13. Okay. And of course, all of our decision variables have to be non-negative. Now, if we put this into Microsoft Excel, this is what it will look like. And of course, I have all of the equations in modeling this together. So we have everything laid out, and pretty much from there we just run the Excel solver and we will get what we need to here in the yellow columns here. And we see once we do that, then we know that we need to start activity A and B from the start. Activity C needs to be after week 1. Activity D needs to be 2 weeks after that. And of course, D and E need to run at the same time. 5 weeks after that, then activity F needs to start. G needs to start a little bit before that. And of course, H would be the last thing. And then of course, by how many weeks are we going to crash? So for activity A, we're going to start at the beginning, and instead of making that a 2-week activity, we're going to make it 1 week. And similarly for activity B, we're not going to crash that at all, so we keep that as normal. And of course, the only other activity that we decide to crash is activity G. We crash that down to 1 week. So of course we do that. We find out that information by basically just running our Excel solver here, and I won't get into too many details on that because at this point, if you've been watching the videos, you kind of know how to run the Excel solver at this point. And so the last thing I want to say is, now that we have all this information together, we could use Microsoft Project to go ahead and put all this information in and track it and keep it going. And so I won't get too deep into Microsoft Project. That's a whole nother issue, but for those of you that are taking the course, it'll be kind of self-explanatory on how to put everything in. And if you're just watching this for information, I'm pretty sure there's other YouTube videos on Microsoft Project so that you can see how to take all this information and enter it in and use it to track and monitor. So thank you so much for your time, and I hope this video helped, and take care.